Because first, Michael Shearer will continue for another 45 minutes, and we have a brief coffee or tea break, and then when they come in, we'll speak about
Okay, good, thanks.
Michael.
So in the first part, I basically talked about surfactants. So now I'm going to talk about the rest of the title. So it's going to actually spread on the thin liquid film. And as I indicated, this picture basically shows a result from the experiment, but we'll come to the details. So the same list of collaborators who...
I should say all the talks will be on the website. They are videotaped, so you can watch them again if you want. And these are sections also during the talks.
Yeah, but you'll be recorded as well. So, so maybe I should repeat that the first part of the talk was to do with surfactants, and now I'm going to talk about the rest of the title. Right. So, otherwise, this title slide is pretty much the same as you saw. And here's the outline again. So I'll tell you a little bit more about surfactants, but mostly I'll talk about the experiments. So what we do, how we do the experiments, and what's new in the experiments. I'll talk about PDE from lubrication theory. Actually, I slipped in a slide that summarizes lubrication theory, because I realized that most people probably don't maybe have a vague idea about what it is, so I'll show you in some detail. We have some mostly simulations, some analysis, and then when we compare to the experiment, so we find some discrepancies, which I'll talk about and list, and then a conclusion slide speculates on what might be wrong that fixes this, how you should modify the model or potential avenues for looking at different models to try and get better agreement with the experiments. So this part of the experiments was motivated actually by wanting to look at the effect of surfactants on Faraday waves. So in Faraday waves, you have a table that vibrates up and down, and you can control the frequency and the amplitude, or if you like, the acceleration. And you get these lovely patterns. This is without surfactant, so you can get all sorts of different patterns of the free surface. So this is just visualized by shining a light over and taking photographs. Actually, we've got movies of these patterns. And so one question was, how do they influence the onset of instability? Because if you just move the fluid layer up and down like this, nothing happens. It just stays flat. You don't see any patterns. But if you start doing this, jiggling it fairly violently, then you start to see patterns. And the evolution of how you get to these steady state patterns is kind of interesting too. But that's another topic. We were interested in the effect of surfactants both in onset and their influence on the patterns. Okay, so here are beginning results about onset. This is data from Stephen Strickland, the graduate student who's working on this project. There's a classic paper of Chen and Vinyals. There are lots of theoretical papers going back to Benjamin and Ursel in the 1950s on when these patterns arise. This is without surfactant. And this paper, Chen and Vinyals, does a very detailed study, including all sorts of effects that were not included in the original studies. So the Chen and Vinyals prediction with no surfactant is this line. And so we use that to sort of calibrate the experiment, and the data from the experiment with no surfactant are these purple triangular things. So pretty good agreement. But then when you add surfactant, so gamma here is the surfactant concentration in micrograms per centimeter squared, you see that if you add any surfactant, these are pretty weak concentrations, you get a much higher onset. So I should explain. There's a driving frequency here, how many hertz you're driving the table at, and the onset acceleration is sort of how violently you're driving the table, or the amplitude of the vibrations, if you like. And so there's quite a striking influence of surfactant on the onset. But the trouble was that we couldn't look at we couldn't look at the distribution of surfactant within these patterns, because if you think about it, the timescales are very short. So the fluid's sort of sloshing around like this, and the surfactant's sloshing around as well. And to keep track of where it is with fluorescence, you have to have an exposure time of the fluorescence on a timescale that's comparable to the vibrations, but long enough that you capture enough photons that you can see something. And we weren't able to do that, at least initially. So we want to do that, but in the meantime, we thought we'd try and set this up, the visualization of the surfactant, on a slower time scale, and that's why we looked at spreading. Now the other thing, there's a list of points here. So one thing is that the lubrication theory for this thin layer of fluid does not include any inertia, but even the original papers on Faraday waves depend on having inertia. So the acceleration I just showed you comes into play, and that's where the inertia is. So lubrication theory, as I'll show you again, involves Stokes equations, not the Navier-Stokes. The other thing was that if we look at very thin films, they tend to de-wet. That is, as the fluid's sloshing around, you'll get dry patches appearing, and then the fluid dynamics is much more complicated. And especially when you put surfactant on to lower surface tension, it allows the fluid to de-wet even more readily. So we had problems with the fluid de-wetting under vertical oscillation. All right, so this idea of including inertia, there is a way to do it without surfactant. It was worked out by Cherda and Tirapedui. It's a somewhat ad hoc, I forgot Royas in Argentina, this paper in 2010. There are some aspects of this paper that are a little bit suspicious. Basically, they use Taylor series expansions for velocities and then just sort of plug into an approximation. It's not really an asymptotic analysis. But they do manage to include the next order terms, the inertial terms, and allow slightly deeper fluids, which would help with this de-wetting problem. Okay, so this is a project underway to include Reynolds number, which measures the amount of inertia you have, and allowing a deeper fluid. Okay, and then this was the comment about visualizing the distribution of surfactant. Okay, so then we went to spreading dynamics of just a layer of surfactant on a thin liquid film. So before I describe that in detail and some of the theory, let me tell you a little bit more from this paper of Tsukhanova, Granger, and Selesi that I mentioned in the first part of the talk. So here's the surfactant that we work with. I promised you 1.5 lines for the description. So the DPPC is in blue, and then there's this fluorescent tag, NBD. It's in the 12th position in the carbon chain. And the numbers here actually tell you where the various compounds are, where the various molecules are within this rather complicated molecule. And again, I'm not going to even attempt to read that description. That's why we have this abbreviation. So here's some text from Tsukhanova, which it's kind of interesting, although I don't understand all the words, and neither I'm sure you won't either. But let me just read it to you, because it has some content. So phospholipids covalently derivatized, so that's the bit I really don't understand, covalently derivatized with dichromophores, that's this NBD thing, are popular probes for fluorescence imaging, which is what we want to do, and photochemistry studies on surfactant, colloidal, interfacial, and membrane systems. So this is quite a broad range of applications. Several phospholipids are commercially available. That was the Avanti Polar Lipids company. And covalently attached NBD with covalently attached NBD groups. They've been widely used over the last 3 decades, now 4 decades, as fluorescent analogs of native phospholipids. That basically means lung surfactant or biological surfactants, to study the properties, spatial organization, right, which we talked about, and distribution of phospholipids and proteins in monolayers, bilayers. That's where you have a layer of molecules and the hydrophobic tails are sticking up, and another layer where the hydrophobic tails are sticking down. That would be a bilayer. And biological membranes, which are typically built out of bilayers. All right, so even more on surfactants. So this was the comment that I made actually in the first half, that the effect of this fluorophore, the NBD piece of the molecule, is a little bit subtle, that it really influences the properties of the underlying molecule, the DPPC. Okay, so let me talk about the experiments. Right? So I'm going to talk about the experiments on and off for a while, sometimes in combination with simulations. This is the experimental setup in a schematic. So from the side, we have an aluminum well, aluminium. It's an American well, so it's aluminum. Right? So it's an aluminum well that contains this thin layer of fluid, a glycerin, and in the middle we have a ring. And inside the ring, we deposit some fluorescent surfactant. So that's why it's bright green, because that's the color of it. And it's dissolved in chloroform, as I'll explain. We have to wait for the chloroform to evaporate, and then we lift the ring. We visualize the height of the free surface by using a laser sheet. It shines in from the side, and the image that we get on reflection looks like this. There are actually multiple reflections, but the top surface is roughly the shape of the free surface. After some optics, you can actually see it more clearly, and I'll show you those pictures. The surfactant, when we lift this ring, the surfactant spreads, and here it is at a particular time. So the scale here is 1 centimeter. And we visualize simultaneously both the free surface height with this line. So we're sort of assuming that it's rotationally symmetric. It looks as though it is, right, from the spreading of the surfactant. And simultaneously, we visualize the fluorescence. Here it's shown brown, but in other pictures it's green. So I made a comment here that Stephen went to a lot of trouble to optimize the optics so we could visualize both at the same time. Right? You have to be careful about absorption and emission spectra and the filter. You have to tune it to the filter that you're using on the camera. Okay, so there are similar experiments. There are a whole range of experiments, actually, that are done with this spread to try and see the spreading dynamics. Here are two configurations. The Ball and et al. Used the similar surfactant and a similar setup. They didn't report much about the spreading of the surfactant. This is the shape of the free surface compared to simulations. And then there was another, Dussault et al. 2005, used a different protocol where they just dropped some surfactant, in this case oleic acid, on glycerin. And they tracked the shape of the free surface using this moire topography. So you draw lines and the fluid distorts, the fluid height changes. Here's a profile of the fluid height, and it distorts the optics, and then you have to do an inverse problem to deduce what the fluid surface looks like. This dark thing here is just a dropper for the surfactant. All right, so here are some more details for the experimental physicists in the audience. We take a certain amount of glycerin. So here's the amount, 38 milliliters. It's almost pure glycerin, and it fills the dish to about 1 millimeter. Okay, so it's a pretty thin layer of fluid. There are experiments done with much thinner fluids where you see all sorts of fancy fingering phenomena, and you have to use different types of optics, and again, you have to be careful of de-wetting. We're working with what are really moderately thick thin films. The ring that constrains the surfactant initially comes in two sizes, and 8 millimeters or 14 millimeters, and there's slightly different behavior depending on those two radii, and one is better suited for higher concentrations of surfactant. That's why we use these two radii. All right, so a certain amount of NBDPC is deposited, for instance, 18 microliters, in a chloroform solution. And to give you an idea of so we talked about surface pressure against the area occupied by molecules. This gives you an idea of how many molecules we're talking about. So this small amount of NBDPC that we're depositing, say typically 18 micrograms, corresponds to 10 to the 16 molecules. Right? So we don't measure things in molecules, we measure things in micrograms. And then we have to wait 6 minutes per microliter for the chloroform to evaporate. Then we have to wake the graduate students up who are running the experiments, right? Because it's a tiny amount of chloroform, it's very safe. Lift the ring using a monofilament. So monofilament is a long word that means fish. So this is a fish line with an overhead pulley, right? So it's just a thin line, nylon line, and pull it up with some so reasonably carefully so that it doesn't disturb the fluid too much and it doesn't create a bubble or a free surface. In the most recent version of the experiment, this is all automated and it's apparently much more reliable, although I haven't seen the experiments with that automation. We record the height of the film, so we're going to assume that there's axisymmetric spreading. So this is in plane polar coordinates, just depending on r and time. So this is from the laser line. Right? So we have to do some optics to get the height. And then the distribution of surfactant. So there's a fluorescence intensity, which is related to the surfactant concentration, but it's not necessarily linear. In fact, it's not nonlinear at higher concentrations. But in any case, we can back out the distribution of the surfactant. And then we average the fluorescence intensity azimuthally, right, in circles. Of course, it's all pixelated, so you're averaging over pixels, roughly in a circular geometry. And we get the surfactant concentration as a function of just the radius and t. All right, and again, to just sort of to orient you as to the relative values of different physical parameters, the density of glycerin is 1.26 grams per centimeter cubed. We have a viscosity, which is also measured accurately. This is in pascals times seconds, Pascal seconds. And there's a surface diffusivity of the surfactant. So you've got these molecules sitting on the free surface. They're diffusing around with Brownian motion. And there's an effective diffusivity, which is really quite small. And even after non-dimensionalizing, this effect is small, and we mostly ignore it. Or in numerical simulations, we include it actually, but it has virtually no effect. The surface tension of clean glycerin, so this is sort of a baseline for the surface tension, is in dynes per centimeter here. We talked about millinewtons per centimeter in the previous talk, but this is the value. And I seem to have an extra arrow here. And the surfactant contaminated surface tension, so the minimum surface tension is 35, right, dynes per centimeter. So we've got quite a range from uncontaminated to contaminated surface tension. The surface tension doesn't go down to 0, it goes down to about 35. So this is the change in surface tension. This is actually related to a sort of driving force given by the surface tension gradient. And so that's a parameter. That's like it's called a spreading parameter. That's why it's capital S. Okay, so that's just the difference here. And then the critical monolayer concentration. So above this concentration, the surfactant molecules form multiple layers. Right? They can't all squeeze into the space, so they sort of clump up. It's thought actually that they form ridges first, and then they form bilayers and do something fancy. So that's an important parameter for us. And I'll show you experiments both above and below this critical monolayer concentration. The initial fluid thickness is about 1 millimeter, and the lateral dimension of the ring, so this is actually a length scale we'll use, is like 8 millimeters. 1 centimeter, excuse me, 10 millimeters. Anyway, and so, yeah, so then we're going to non-dimensionalize. So dimensionless variables in height, we scale by the beginning thickness, H0. And the surfactant concentration is scaled by this critical value. And the horizontal length scale is scaled by the ring radius, not the size of the apparatus. All right, so we did various experimental runs. There are 6 listed here. I'm just going to show you a couple. We did many runs which are below this gamma C, and a couple of runs. One of these, at least one of these, is an old run from several years ago, above gamma C. So this is where you've got a ring, you've got surfactant inside, and it spreads outwards. And, I think I might have, well, we'll see. And there's a little subtlety here in that this ml is the mass of lipid that's deposited, and the gamma 0 star is the deposited concentration. But some of the surfactant may be deposited on the ring as it's lifted up, so it's not necessarily quite accurate as the initial mass or the initial concentration. Okay. Here, this is what I was looking for. So here's a run with the high concentration, And the ring is initially in this dashed white line. That's the location of the ring. And so the fluid is spread out, and you can see that, so the idea is that the surfactant is spread out, and the fact that we've got a low surface tension here, a high surface tension here, means that the fluid surface is being dragged in this direction. It's a Marangoni stress. When I talk about the lubrication approximation, we'll see, in the equations, we'll see where this effect comes from. And so fluid is being dragged to the edge, and that's why there's this ridge in the fluid height. You can't see it very well here. In the plots of the experimental results, it's a bit more visible. At Harvey Mudd College, and actually to some extent at North Carolina State, there's an inward spreading experiment where the ring is initially here and surfactants outside, and so the surfactant spreads inside, and these two ridges come together, and they either coalesce or they don't, and the hole either closes or it doesn't. And there are more details about this that I'm not going to report on. It's also a very interesting experiment, which is not in agreement with the mathematical model, for somewhat different reasons as well. Everybody's quiet. Feel free to ask questions. All right, so now after the various bits of image processing, we have experimental results. This is actually from this earlier paper of Karen Daniels and various undergraduates and graduate students. So what's plotted here is the radius from the center, horizontally in millimeters, and the height of the free surface, that's the red curve, so the height in millimeters. And in green, and this is the scale over here, in micrograms per centimeter squared, the surfactant concentration. So remember, this is after averaging the fluorescence azimuthally. So this is after some short time, so that time 1 second. To start with, when you lift the ring, you can't see anything. The ring's getting in the way of the camera, and it's very bright. And so you don't really see anything except the ring. So this is after some initial transient. The surfactant is spreading out, but it's still at a high concentration near the center. The location of the ring is this dotted line, just to give you a sense of where that is initially. And then it's spreading out here, you can see. So what's interesting here is that there's what we call a Marangoni ridge. This maximum is propagating outwards, and here it goes. And the surfactant has a distribution which we weren't expecting. That is, it has a long sort of flat layer, and there's a little ridge near the leading edge. And the peak in the film height is catching up to the leading edge of the surfactant. By this time, they're almost in the same location. From this angle, they look as though they're exactly in the same location. I'm sure they look different from over here. Oh no, they're almost exactly in the same location from over here too. Right. No perspective came into play there. And here's that long ridge that is quite remarkable, and then a little lump of surfactant, it seems, at the leading edge. Okay, so here is the fluorescence intensity. This is actually from a more recent run where we were looking carefully at low concentrations. I don't think I actually put the concentration in here. This is at a low concentration. This is now the intensity of the fluorescence signal at different times. We ran it for quite a long time. You can see that, so this is a low concentration run, and the leading edge is hardly moving actually, but we have this long ledge. So this is after a comparatively short time, and these features are decaying, and so is the ridge inside the ring. Okay, so now I'll talk about the modeling, and part of the modeling depends on defining dimensionless parameters, and then you compare values. And so it's not too hard to see which is the small dimensionless parameter in this slide. But so in non-dimensionalization, you scale everything in sight. So you scale space and time, pressure, velocity, the surface height, and so on. And what comes out are equations with these dimensionless groups. And I'm not going to show you the non-dimensionalization in detail, because it is actually quite messy. But these parameters measure the competing effects of various quantities. So this parameter beta, for instance, has gravity, and it has this spreading parameter. So it's a competition between gravity and surface tension, changes in surface tension, in fact. And so it's a fairly large parameter with these physical parameters. Capillarity measures surface tension versus this spreading parameter. So it's actually the effect of surface tension and, as we'll see in the modeling, the effect of the curvature of the free surface. Capillarity comes in to the curvature, which influences the pressure. The Peclet number has to do with diffusion. The surface diffusion is ds, that's dimensional. And so there's a competition between surface diffusion and viscosity and the driving force from surface tension. And it turns out, so this is called a Peclet number, the effective non-dimensional diffusion constant that comes in front of the Laplacian eventually is actually quite small. Now the interesting thing for us, which is the reason I put it in boldface and in red, is that there are no free parameters in this non-dimensionalization, and so we get a time scale that is about 1/2. So this is the experimental time scale, the real time, and this is a scaling, a dimensional scaling. So it has dimensions 1 over time, and you get a dimensionless time scale. But this says that the simulation time scale, if you run simulations of the PDEs, should be on a time scale that's 1/2 of the real experimental time scale. Okay, now, so yeah, the PDE model is based on the lubrication approximation, and it's a very complicated system of 2 equations. There are 2 variables for the height and the surfactant concentration. Again, it's plane polar coordinates, no dependence on theta. So I thought actually that this is a bit hard to digest, even though it's in several colors. So let me give you a little idea of where these equations come from without doing all the details. And I just rather threw this together, actually, and so you can see I made a bit of an error up there, and maybe there are some other errors. But if you spot some errors, ask me a question, and I'll say, oh, that minus sign should be a plus sign. So you'll see. So here's our situation. I'm just going to look in 2 dimensions. So I've got x and z. So this is a whole layer of fluid. I'm only going to look at putting surfactant down on a line, if you like, and it's going to spread out to the left and the right. So we'll get these ridges, and then it'll presumably flatten out to some height, x going to infinity and minus infinity, or the edge of the aluminum dish. And so this is the glycerin, and here's the free surface, z equals h of x and t. And so the lubrication theory is based on Stokes equations. Here are Stokes equations which match the gradient of pressure, so the forces are on the right-hand side against the shear rate. So this is the shear stress on the left-hand side, and mu is the viscosity. So this is really the divergence of the strain rate tensor times viscosity. And the pressure gradient is just because fluid likes to go from high pressure to low pressure. So in a continuum, it goes from, it follows the minus the gradient of the pressure. So I've actually moved this over to the right-hand side. And then this is a body force representing gravity, which is going straight down. Right, so if z is going up, there should be a minus sign there. And I may have got it wrong even so. The dimensions here, the height of the film is a small number, right, capital H, and the width, it's actually the ring size, is a comparatively large number, so the dimensionless aspect ratio, h over L, that L shouldn't be there, by the way, epsilon equals h over L, is a small dimensionless parameter. So for this 2-dimensional case, if we use epsilon as a small parameter in Stokes equations, we can get rid of a lot of terms because they're higher order in epsilon. So I won't go through that, but there are 2 equations here, right? Because U has 2 components, has a horizontal velocity and a vertical component of velocity. And I've written the 2 components of the Laplacian of U, so the Laplacian acts on each component separately. And the only term that survives in the horizontal part, so this is the first component of the velocity, is the double z derivative. The double x derivative is smaller because d2 by dz squared has something like a 1 over epsilon squared or a 1 over h squared. So it's bound to be larger. The vertical velocity is smaller actually partly because of this divergence-free condition. So this expresses, if you're not familiar with it, this expresses the incompressibility of the underlying fluid. The second equation from Stokes' equations, again, here's the component of the gradient of p, the z component. And the only the Laplacian term doesn't survive at all because the w component of velocity just is smaller. And so the only thing that you get is the contribution from the body force, from gravity. So we can integrate these equations, right? I know how to integrate dp dz equals a constant. And what you get is that p is linear. And now we want the fluid to be, so p is linear. And so here's the expression for p after I put in a boundary condition. So the boundary condition actually is very important. I've got the effect of gravity here, and there's a constant of integration, which is this term, and this term. And I get that constant of integration by looking at the free boundary. So at the free boundary, as we talked about in the first lecture, there's a jump in the pressure due to surface tension. Right? So you've got this curved surface. The surface tension is acting tangentially on the sides, and it gives a net force downwards. And that's what gives the jump in the pressure. Okay? And so it's related to the curvature. That's this term here, surface tension times curvature. And here I've linearized the curvature, right? So the curvature here would have a 1 over the 3/2 power of 1 plus hx squared. So this is the linearized expression for the curvature, surface tension. And so here's the pressure. It depends on x because the height h will depend on x and t. It depends on t as well. Okay, so then we can go into the second equation. So we solved this equation. We go into the second equation, and we take dp dx. So the only place that x comes in, so first of all, the z goes away. So there's no z in dp dx. And we get derivatives of h, and we get a third derivative of hxx. Okay? And in principle, we could get derivatives of gamma as well. Okay, so then we get, we can integrate this equation as well, because it's a second order equation I can integrate twice. So here I've integrated it twice, so we get a z squared. The constant term here is 0 because I want to have a no-slip boundary condition on the solid surface, on the solid substrate. Okay, so A actually comes from another boundary condition, the free surface, called the kinematic boundary condition, which just says that the fluid molecules in the free surface flow along the surface. Right, so it's just a boundary condition that comes from that. Anyway, so I've got this velocity and I've got the pressure, and now I need to write down equations of motion, which are written over here. So the equations of motion are there's fluid flowing, say, to the right here, and as the fluid flows to the right, it's going to influence this free surface. So if I have more fluid coming in from the left than is leaving on the right, I'll get a higher free surface. And so that's a very common conservation law. You have a velocity, a horizontal velocity. In this case, it's going to be a depth average velocity, and the height responds to that transport. Okay, if u bar is a constant, this free surface just travels along with constant speed, at constant speed u bar. All right, so that we need one depth average velocity, and then the surfactant molecules sit on the surface. I didn't have time, unfortunately. I just threw this together. I said the surfactant molecules sit on the surface in some arrangement with a concentration gamma that depends on x and t. So the fluid is moving along the surface, and it will transport the fluid molecules with it. And so in this model, we're going to make a very naive assumption, but it's been made for decades, that the surfactant molecules travel with that surface fluid velocity. So again, there's a transport equation here, but it's with the surface velocity, and then here's the diffusion component. So this is the spreading of the surfactant molecules due to diffusion, the Peclet number. All right, and so we've got these simple equations, but u bar and us have h and derivatives of h involved. So here's the definition of u bar, you depth average, right? So you integrate in z, divide by h, then you multiply by h again. So, right, we've really just got the integral of u buried in here. And then the surface velocity, you actually evaluate that horizontal velocity at z equals h, and then substitute into this equation. All right, so that is, this looks incredibly simple, right? But in fact, that system of equations is the same as this system of equations, except that here I've put in radial symmetry, and all of those x derivatives became gradients in R. Right? So that's why we've got these geometric terms with R and 1 over R. Right? But the number of derivatives are still here. So there's one other thing that I didn't really tell you about, and that is this Marangoni stress that's created from another boundary condition of the free surface. So this says that if we've got a gradient in the surface tension, and the surface tension depends on the surfactant concentration. So here's a gradient. If that's non-zero, then we get a driving force. So this is another transport term, nonlinear transport term, that contributes to the horizontal velocity. And it shows up in the surface velocity as well. So the way to read this is that this is dh dt. There's an h in here times a contribution to the depth average velocity. There's an h in each of these terms that multiplies a contribution to the horizontal velocity. And here the colors just mark out the different effects. So there are two gravity terms. These are curvature terms, where kappa is the capillarity. Here are these high order derivatives that come from the curvature. And then here's the surface diffusion of the surfactant molecules. Okay, so in principle, it's a simple model. It's just from straight lubrication theory. There is no inertia, and we get these equations. So the thing that I'm interested in, actually, which I'm not going to go into, but just to give you a little bit of information about my particular interests, I would set all these parameters to 0. And then you've got a nice, simple system which looks like a hyperbolic conservation law, or a scalar equation, as long as you know the surfactant concentration, because it's just a d by dr on a function of h. And then you've got a simple transport equation for R, which has h, which you could get in principle from the first equation. But in fact, we need to simulate this entire system using implicit finite difference methods, is what has been done. So I'll show you a little bit of that. Are there any questions about lubrication theory? Or let's see, do I have another 5 minutes or something? Is that it? Okay, all right, I better move along. Okay. I showed this picture in the first lecture that we actually have results that calibrate surface tension against surfactant concentration. So this is the equation of state. But the equation of state that I'll show you, that we use in the simulations that I'll show you, look more like this blue curve. So this is one possible source of error in our simulations when comparing to experiments. All right, so here's a typical comparison. The red dashed curve is the experimental result for the propagation of the free surface. And so this is the particular time 5 seconds. And the blue curve is a result of simulations. So we get wonderful agreement, but we have to double the time scale. So the predicted time scale was 1/2. In order to get this agreement, this level of agreement, we have to have that time scale be 1. So there's no factor of 2 in our calculations, in case you were wondering. So this is a real disagreement. The other thing, which in a way is more striking, is that the surfactant concentration, when computed, when simulated, is very smooth. And we have a readily identified leading edge, which agrees in this timescale pretty well with what we observe in the experiment. But we've got this ledge that's opening out. We don't see this feature at all in the simulations.
How do you define the leading edge if you have diffusion?
Right. So in the simulations, there's a threshold that we get. In the experiments, you can see where it is. So you go between the experiments and the fluorescence plots and decide where it is. I think this plot actually was without delta, so there's a sharp leading edge. Okay, so then we tried changing the initial surfactant profile. So here it is inside the ring, and then drops immediately to 0. There's slight smoothing here. And another one we tried was, well, maybe it's collected more around the ring on the outside, so you've got a distribution something like this, and then maybe some near the ring, and there's more, further inside. Whatever we do to the surfactant concentration, we get, essentially the same result, the same smooth distribution as time goes on. The height profiles still agree pretty much. I mean, it's not perfect, but with any of these initial surfactant profiles, the height does fine and the surfactant stinks. Well, it doesn't literally stink, but it doesn't look good. Okay, so so this was just to emphasize that point. So we tried a hybrid model where we take the experimental surfactant distribution and we try and recover the surface profiles. Now we don't have any problem with the time scale because it's set by the distribution of the surfactant. And so you take the surfactant concentration. We're doing a little bit of processing with splines here. So here's the experimental profile in green, a very noisy signal. And it looks as though there are two regions, right? There's sort of a flat region here and here, and then it drops to 0. And so we did that at various times, and you fit polynomials, interpolate at various times. You can put into the height equation. So then we know gamma. We just have to compute height. Gamma, of course, depends on R and T. And so what happens is you compute these height profiles. And again, the fit is not great, but at least we're capturing the idea of the propagation at the right speed with a maximum that's more or less in the right place. So this suggests that what the real serious problem is with the surfactant concentrations, of course. But so the height equation should be just fine. And what we need to fix is how we model the propagation of the surfactant. These are some more results actually from high concentrations of surfactant to show the propagation of the Marangoni ridge, that maximum in the fluid height. The simulations are in black dots, and the many runs, it's easier to track where the height is. Many runs give a slope around 0.3, which actually differs a little bit from theory. But the surfactant spreading is right on 1/4, which is actually predicted by earlier theory of Jensen without capillarity, gravity, and diffusion, but nonetheless. These effects actually just smooth this result a little bit. They don't change the experiment. One thing I was going to remark is that these are log-log plots. You might not be familiar with log-log plots, but they're used to detect power laws. So if R of t goes like t to the lambda, right, so that we'll conjecture it goes like t to the lambda, if I take the log of both sides, then log R goes linearly with log t, and the slope of the line gives you the exponent. Okay, so if you haven't seen that before, that's a quick explanation. Okay, so here are some more plots of the surfactant at high concentration propagating. These are actually very recent experiments, and there's this long ridge that appears, and then at low surfactant concentration on the same horizontal scale, it hardly moves, and the interesting thing is the concentration is almost the same as the level of this ledge. And here are spreading rates. So another thing that's interesting here is that at low concentration, the spreading rate is at about t to the 1/10, much, much slower than predicted by theory, which is designed for low concentrations. And at high concentrations, we get 1/4, as I showed you just now. I was going to show you a couple of videos, but maybe I should just end with those. I think I can just play them here. Right, so this is the low concentration case. You can see that the surfactant is barely moving, spreading. You can see here that here's the edge of the leading edge of the surfactant. It is moving, but very, very slowly. So that's that 1/10. I think I just do that. No, I don't do that. Oops. That's the wrong thing to do. I should just stop. Right? Okay, now I'm really in trouble. There we go. Okay, and then at high concentration, it looks rather different. It spreads rather rapidly, and you see this long ledge. You see a higher concentration in the center, and it continues to spread. Okay, so again, I'll get out of that. Okay, great. Right, so here are some references which I thought might be helpful. We have a few papers, and here are some early papers. And here's a really good review by Krasser and Matar of dynamics and stability of thin liquid films. Lots of information, not only about surfactants. And then finally, conclusions. We've got problems with matching the model to the experiments. It may be because the fluid layer is too thick. It could be because we're not modeling the propagation of the surfactant properly. Or it might be, as I sort of indicated in the first part of the lecture, that there are phase transitions that are affecting the equation of state, or maybe more subtly than that, and affecting the propagation, the transport of surfactant. Thank you.
I had a question about the two videos that you showed then.
Yes.
You said in the low concentration case it shows t to the 1/10.
Right. Yeah. This slope. Right.
If you leave the
So this is at a slightly higher. This is at a higher concentration actually. So it really just applies to these plots. Yeah. Go ahead.
If you leave the high concentration one long, you just recover the same behaviour as you saw at the start of the low concentration one.
Well, of course we're on a fairly small dish, so I think you'd have to have a much bigger dish to see that. But yes, that ledge continues to drop, and then you would expect to see it to slow down, possibly. Yeah, but I don't know. You can see here it's continuing on at a higher rate. Yeah. Yes.
You looked at the parallel, the height of the
Of the ledge.
yeah.
No, we haven't looked at that actually. No, that's a good point. Yeah. But I think it'd be interesting to see if that's just sort of a geometric effect, right? You've got this disk that's spreading out. You should be able to figure that out just by the geometry.
Mass conservation.
For mass conservation, exactly. Yeah.
And so your simulations are done with delta 10 to the minus 5?
Delta equals 10 to the minus 5, yes. Some of the simulations are done with delta equals 0, but that's where we want to compare with to really assess the effect of the surface diffusion. Or if we want to really get a sharp point for the leading edge of the surfactant. It's a little like the second equation is a porous medium equation if delta is 0. So it degenerates at gamma equals 0 and has a finite propagation speed.
Listening mic again.
Okay.